Good afternoon, everybody. We're just going to wait a few moments while all the participants are joining. Okay, welcome to the final of today's webinars from Smart Vision Europe. This afternoon, we're looking at how to interpret significance tests. This is a very popular webinar that we've been running over the past couple of years. And it's very much looking at thorny issues around significance tests, p-values, that type of stuff, and trying to give people some sort of steer or guidance through that and to put things into context within the next hour or so. Again, for those of you who haven't joined any of our sessions before, we do record these sessions, so you'll be able to listen to them again. Secondly, there are quite a lot of slides in this one. There aren't normally as many slides in our sessions, but there's quite a lot of slides in this one, and we will email a link to you to download those materials after the session's ended. If you think it's particularly useful for colleagues who are unable to attend today, it may be possible for us to rerun it for them. The best thing to do is just drop us an email or something like that and ask us, and we'll see if we can set up another session. And with regard to asking questions, with all the lines unmuted, we ask you to use the chat panel. In this particular session here, there's quite a lot to pack in. I'll probably not be reading the chat as I'm going along, but I promise to follow up afterwards with any questions that you do write into the chat panel. Okay, if you don't know who Smart Vision Europe are, we are a premier accredited partner to IBM and also a company called Predictive Solutions and Data Robot, and we specialize in statistics, advanced analytics, and big data technologies. We also work with open source technologies like R and Python. And we're made up of a team of veteran consultants and salespeople from SPSS Incorporated, stretching back over the last 30 years. So I've spent a lot of time over the last 30 years working with companies like SPSS and SAS and IBM as a consultant and statistician. So this is something that we're very familiar with as a subject area. And it's also something we're very familiar with providing teaching and training around, because we do that on a regular basis. We have very deep applied experience of applying advanced analytics and classical statistics to lots of different vertical sectors and lots of different applications. I'm not going to go into all of them at the moment, but suffice to say that over the last 2 or 3 decades, there are many different examples of where we have applied our learnings around this area. Okay, so our agenda today is we're going to start off by the term significance testing, why that's so problematic, the historical context around that. And then we're going to look at inferential statistics and how significance testing relates to that. Then 4, we're going to move on to interpreting p-values, probability values, and what is the correct way to interpret them in the frequentist tradition. And then we're going to look at 3 examples. We're going to look at, well, let's look at the chi-square test. How does that actually work? Correlations, I'm going to dive into that, and then finally end up looking at interpreting confidence intervals correctly, because a lot of these are just commonly misinterpreted types of output, but they're very, very popular procedures that have been run, not just these days, but for the past 10, 20, 30 years. Okay, let's get straight into it and deal with this issue of significance. Most people talk about significance testing. So right from the get-go, significance is a very troublesome term, and the person who came up with it is kind of the godfather, if you like, of what is known as classical frequentist statistics. These are the statistics that we've all been taught in university. These days, you'll hear people talking about Bayesian statistics, and that's something for another discussion at some point in the future. But suffice to say, Ronald Fisher very much the grandfather, the godfather of what we call frequentist statistics, and he introduced the phrase tests of significance. Okay, so that's from a book he'd written in 1925. Unfortunately, saying that something is statistically significant, however, is likely to be very much misunderstood, because when something's significant, it does kind of sound like something is notable, something's important. And in this context, significance definitely does not mean that. Sometimes it doesn't even mean it's technically reliable. And even the term test itself, when you say a test of significance, is slightly problematic. It's almost like when there's a test, a measure or an estimate, if you like. It's sometimes an estimate of probability. Significance tests are probably more properly described as probability of evidence estimates, but I don't think is likely to get adopted anytime soon as a common term or a common turn of phrase to describe them, but it's technically more accurate than saying test of significance. And the people who are responsible for much of our thinking around what's called the frequentist tradition, which is, as I say, classical, what most people's understanding of classical statistics, are Ronald Fisher and Carl Pearson. Carl Pearson's son, Egon Pearson, who worked closely with a guy called Jerzy Neyman. So Pearson and Neyman are used a lot together. They didn't even necessarily get on with each other. They didn't necessarily agree with each other. So what you end up with is sort of smorgasbord of approaches and lots of different terms, which most students, psychology students, social science students, students of stats will recognize terms like significance, terms like confidence intervals or maximum likelihood or rejecting or accepting hypotheses or null hypotheses and F tests and chi-square and Z tests and all that stuff. It all comes down to a relatively small number of people who are responsible for that. Fisher being, I think, the original progenitor and really much the engine behind a lot of it. And they argued, and they had different approaches. If we look at inferential statistics and significance tests, where does that come in? Well, as you know, when we're describing data in a file, we might take something like an average, or say a mean, say, or a median or something like that. And we'll say, what is the average value in here? And if we're simply describing what's in that data set, then that's called simply a descriptive statistic. It's just a way of trying to summarize that statistic. What proportion are left-handed, what percentage are male, that type of thing. So a statistic is a characteristic of a sample. That's the most important thing. But samples come from populations. And populations are in many ways all of the data that you could have gathered if you had infinite resources. So think of a difference between taking a sample of water from the Indian Ocean as opposed to, having information about the entire Indian Ocean. So the sample is the sample, and the population is the ocean. And the equivalent of a statistic, given that a statistic is a characteristic of a sample, the equivalent of that in a population of all possible values is called a parameter. So if you wanted to know the exact average blood pressure of people in the world right now, in the entire world right now, you're not going to get that. That's a population value. A population is a characteristic of a population that would be called a parameter. So the best you could do is take a sample of people, and hopefully it would be a really big sample and it would be a really good sample, and you'd try to take the average from that sample. But that, as soon as you do that, what you're doing is you're calculating a statistic coming from the term state, meaning it's a state of a sample. So how can we use statistics to infer parameter values of a population? So how do we use a sample statistic to say what the real true value is in a population when we only have a sample? Especially when different samples from the same population produce different results. If you were to take your sample from the Indian Ocean repeatedly, and let's say you're trying to measure salinity or something like that, and you're measuring it to, I don't know, like 10 decimal places, it's not going to be exactly the same value every single time. So in the same sense, if we wanted to calculate the mean age of men and women from a given population. We might take one sample and find that the men are 34 and the women are 32, another sample where the men are 33 and the women are 30, and another sample where the men are 31 and the women are 32. They vary from one another. Samples vary from one another. So how do we start to make inferences about what the true values are, what the parameter value is in a population when our sample values and our sample statistics are likely to vary? Well, the fact is that variation is critical here. Statistics is the science of variation. So what is the likelihood that the mean ages are actually the same in the population? We may not actually be able to say, you know, what are the true mean ages in the population, but we might start to ask questions like, well, are they even different from one another? Is the average age for men higher than women? So if you're asking a question like that, you know, somebody might say, well, what's the probability? What's the chance that they're actually the same in the population? Let's start with that. Let's assume that, you know, when you gather a sample and you calculate statistical values from that, the reason you're getting different values for men and women is simply because it's a result of a sample. In reality, in the population, they're the same. In other words, it's just sampling error, I feel like. So hence you may get situations where, you know, the women actually have a higher average age than the men, or where the average age is much bigger. It's 3-year difference here as opposed to a 2-year difference here. So these are the questions that we're using, that we're posing in inferential statistics. We're attempting to make an inference about what's going on. So where does significance come from? Significant doesn't mean noteworthy. Okay, that's the first thing. As we said already, these tests simply indicate that the evidence does not support the assumption there's no difference between certain groups in the population. That's what we would regard as significance when we say we've looked at the evidence, and this notion that there's no difference between the certain groups in the population isn't supported by the evidence. So significance simply refers to that situation when, on balance, you know, there's no evidence to support the idea that there's nothing going on, that there's no difference, everything's the same. And you should bear in mind that significance is measured often with what we call p-values, but these p-values, these probability values, can appear in many different forms. So even within the SPSS, within a single stats package itself, you might see a value like sig, or p equals, or prob, or asymptotic significance. They're actually all the same values, or they're all interpreted in the same way. The labels are different. Sig for significance, p for probability, prob for probability, and asymptotic significance means the probability using an estimated value effectively as opposed to an exact value. So a sig value, p value of 0.001 means 0.1%. You basically multiply it by 100 in your head. A p value of 172 means 17.2%. That's how you interpret it. You turn them into percentages in your head. Sometimes you get p-values where it's just 0.000. That doesn't mean the probability is 0. It just means the probability is too small to display. The p-value is too small to display. So it just shows you the first few digits. And if actually you can double click on it within the SPSS and often see the true value, which might be, you know, 64 decimal places. It might be really, really tiny, but it's never 0. Okay. Or you might get something like 0.03, meaning that there's a 3% chance or 3.4% chance of you being specific in this exact example. So first of all, you need to interpret. You need to know what the actual number is, and you need to convert that into percentages. And you need to appreciate that the number, the key number, this p-value, is labeled in all sorts of different ways. That's basically all we're trying to convey here. If we return to our earlier example and we say, if we assume there is no difference or no relationship between the groups, i.e. you know, men and women, the mean ages of them in this population are exactly the same. That's our assumption. We might find that when we actually collect data and run a test, it will give us a p-value and tell us the probability in many ways that what we're looking at is I guess, I don't know, use the term statistically significant, but the probability that there is no relationship or there is no difference between the two groups. I need to go into that a little bit more detail in just a few moments, what we mean by that. But typically, if you were comparing two averages, you would use something called the t-test. That's what you normally use. So you could calculate t-test for a given sample. We don't know what size these samples are. It might be 100 cases here, or it might be 1,000 cases. We don't know. But if the p-value said 0.111, it would say, it's saying that you would see a difference as big as this 11% of the time in a world, in a universe where the mean ages of men and women were exactly the same in the population. It's saying that this difference is so small that you would see a difference as big as that 11% of the time, even in a universe when the mean ages of these two groups are exactly the same. Maybe you have a larger sample. Maybe you have a much bigger sample, and this time it's saying the p-value is 0.04. Here it's saying you would see a difference as big as that, a difference between 33 and 30, 3-year difference, as big as that 4% of the time in a universe where the mean ages for both groups was in fact the same. Because, as you know, it is possible to flip a coin 10 times and have it come up 10 times heads or 10 times tails. It just doesn't happen very often. Okay, so this is what we're doing here. Here we have a very small difference where actually women are 1 year older than men on average. Maybe this is a really small sample size. Here we would see a difference as big as this, in inverted commas, 33% of the time in a universe where the mean ages were exactly the same. So this is how we're making sense of these p-values. Okay, and we have to bear in mind that different samples and different sample sizes will result in different p-values. So this leads us to what's called hypothesis testing. If you're investigating a relationship with statistics, in our example here, we're looking at the differences between men and women's ages, let's say, in a given population. It's usually because you're curious to see if there's a difference or a pattern. In other words, you have a hunch or a hypothesis. Okay, I think that there's a difference between the average age of men and women in my population. If I say that, that's called my alternative hypothesis, and it's often labeled H1. But in reality, the p-value is focused on the null hypothesis. The null hypothesis is the idea that actually your data supports the idea that there is no difference between the average ages of men and women in the population. They're exactly the same. In other words, HO is always the opposite of H1. And the p-value is always focused on the null hypothesis. In fact, the p-value has nothing to say about the alternative hypothesis. Alternative hypothesis is just something, it's just a reference point. P-value has nothing to say about it whatsoever. It focuses entirely upon H0. The relevant test then calculates a probability that indicates if this null hypothesis is true, how often would we get a result as extreme as the one we observe? That's what it's doing. It's simply looking at the null hypothesis and saying, look, I know that it's possible you can get differences as big as the one you've observed. Maybe it's a big difference, maybe it's a small difference, but it's saying, I know it's possible for you to get that even in a universe where, you know, the mean ages are exactly the same for men and women. But how often in that universe would we get a result as extreme as the one we observe? That's what H1, that's what the p-value is showing us. How small or how large does this probability value need to be before we decide that the data doesn't provide enough evidence to support the null hypothesis? Should it be 32%? I mean, in which case it would be p equals 0.32. Would 32% be a reasonable threshold? We say, you know, if it's less than 32%, we're going to say that's too rare an occurrence to support the null hypothesis. What about 100%? Maybe we should say that, you know, we have to be 100% accurate, so the p-value should really be equal to 0 before we say that there's not enough evidence to support the null hypothesis. Now, clearly, we have to choose some sort of threshold. You have to choose some sort of value, some sort of cutoff point. This is known as an alpha level. This is the cutoff point, and it's actually fairly arbitrary. There's no science behind it particularly. It's just a line in the sand that's been drawn. Ronald Fisher suggested 5%, which is about a 1 in 20 chance. And basically what he actually said was, yeah, in some cases, but 1 in 20 might be appropriate. In other cases, maybe 1 in 50. Maybe in other cases, like 1 in 100. And basically, people only heard 1 in 20 and they wrote that down. And that's what generations of students and researchers have stuck to ever since. So it's unfortunate because it becomes a sort of magic line in the sand when in fact, in reality, it's just an arbitrary cutoff point. But on this basis, if you do choose a 5% level, then you're saying that if the probability is less than p equals 0.05, we would reject the null hypothesis on the basis that there is insufficient evidence to support it, because we would say there is a less, in a universe where the null hypothesis is true, you would see a result as extreme as this less than 5% of the time. And if you happen to think that that's too small a number, you reject the null hypothesis. Now, contrary to a lot of statistical teaching here, I've been trying to be very careful with my language around the null hypothesis. What the p-value does not indicate is the probability that null hypothesis is true. Lots of people have taught that. That's not true. Or the probability that the data were produced by random chance. I've taught that. You know, we've said these things in the past. We just have to be really careful of our language these days, because there's more scrutiny starting getting paid to that. What p-values can do is indicate how compatible or incompatible the data are with our null hypothesis. This notion that that we live in a world where there's no difference or there's no relationship between the variables or the values or the categories that we're investigating. Now, that might sound like semantics. It's not. And the reason is simply that the probability of x given y, of a given b, is not the same as the probability of y given x, of b given a. And you can prove it. It's really simple. You can simply say, well, what's the probability of someone having a driving license given the fact that they are aged 17 years old or over in the UK, let's say? What's the probability? I don't know what it is. It might be 60% chance. I don't know. I don't know what proportion of people aged 17 or over actually have a driving license, but I might guess something like that. The point is that that's not the same as saying what's the probability of somebody being aged 17 or over, given that they have a driving license. Because in order to have a driving license, you've got to be 17. So it's much closer to 100%. So they're not the same values at all, or they certainly don't have to be the same values. Now, that's exactly the same as saying the probability of the null hypothesis being true, given the evidence, is not the same as the probability of getting that evidence, assuming the null hypothesis is true. And that's why statisticians are so dogmatic about the language around reporting a null hypothesis. It is the probability of getting a result as extreme as the one observed, assuming the null hypothesis is true. Null hypothesis is pretty important in these tests of significance. But to correctly interpret any significance test, you have to know the null hypothesis associated with it. So here's an example. The null hypothesis for a chi-square test is that the two variables, usually category variables, are independent of one another in the population, i.e. they are not related in any way. There is no relationship between people being left-handed, right-handed, and let's say whether or not they are vegetarian or not vegetarian. There's no relationship. That would be our hypothesis, our null hypothesis. For a t-test or an f-test, those look at averages, they look at means, and they look at group means. So they're saying that for t-test, they're saying the group means are the same in the population, i.e. they're the same value. So you think that reflex reaction time is in no way affected by alcohol intake. So the average reflex reaction time, that would be a null hypothesis. You'd be saying that any differences I observe are simply, just a fluke, just a random chance sampling error. And you do a test and it says that in a universe where alcohol intake in no way affects reflex reaction time, you would get a result as extreme as this, whatever that result is, X% of the time, and that's what it's doing. For Pearson's correlation value, you'll see this one. This is a correlation that tells you the strength of a linear relationship between two categories. The correlation, the null hypothesis for that particular type of test is that isn't that there's a weak correlation. It's that there's no correlation between them, that the two variables are completely unrelated. And we'll see why this is important to know when it comes to interpreting Pearson's correlation, because we're going to look at an example of that. And then you have tests of what are called tests of tests. So null hypothesis for Levine's test of equality of variance is that the groups have the same standard deviations, that they have the same amount of spread. And that's used often to try and figure out whether or not you can actually go ahead with another test, like a t-test, because one of the assumptions might be that the two groups have the equal amount of variance. And you even have tests of whether or not your data is normally distributed. In a normal distribution test, like KS-Lilliefors, the null hypothesis is that the data is normally distributed, that is the default test. So therefore, a p-value greater than 0.05 would indicate that the data is normally distributed, because you wouldn't have enough to reject the null hypothesis. So you can see why understanding the null hypothesis is absolutely critical, because you got to know what it is you're accepting or rejecting when you look at the p-value. So that's critical. That's one of the golden rules. Let's look at an example of this. Remember crosstabs and chi-square. This was our first one. Null hypothesis per chi-square test is that the two variables are independent of one another in the population. Let's look at that. So crosstabs are a very powerful way to examine relationships between category variables. And the chi-square test is commonly used with crosstabs as an associated statistical test. So if I want to look at the relationship here between gender and people's employment category in a bank, where the sample is taken from a sample of bank employees, but the bank itself actually has many, many other larger group of employees that we couldn't really sample, then we could look at this and we could investigate and say, let's do a little table where we'll put men and women on one side and we'll put employment category in the other, and we'll add up the numbers and have a little look at it. Now, the difficulty here, as we can see right away, is that there's 216 females and 258 males. So it's tricky to compare them because the group sizes are different. So what do we normally do? We add to the frequency counts. What we normally do is we add in percentages. And if we're comparing men and women happen to be in the rows, the gender variable happens to be in the rows, then we ask for the row percentage. And that way we're saying the percentage within gender, percentage within female, 95.4% of the female employees are clerical workers, 0% are custodial, and 4.6% are managers. For the men, 60.9% are clerical workers, 10.5% are custodial, and nearly 29% are managers. So the percentages help us to compare different groups when the group sizes are different sizes, and we can say what proportion of men and women fall into different categories. At this point, somebody might come along and say, yeah, but maybe this is just a fluke. I mean, I know these are quite big differences here, but maybe it's just a random sampling error that's kicked in here, rather than the fact that men are more likely, or seem to be more likely to be managers, and women seem to be much more likely to be clerical workers. Well, something you need to understand about these various counts, these frequency counts and percentages that you can do in a crosstab, is you can calculate something called an expected count. And an expected count tells you how many women you would expect to see if the proportions were equal. If the proportions were if you were controlling for the same sizes, if you were kind of normalizing things out. In other words, here the expected count is 165. It's saying I would have expected to get 165 women in this cell if they weren't biased in any way towards clerical work. Instead, I'm getting 206. And down here for the men, I would have expected to get 197. But in fact, I actually get less than that. I get 157, and so forth, so forth. Now, how is that being calculated? How does it know the expected count? Well, all it's doing is just adjusting. For each cell, it multiplies the row total by the column total and divides by the grand total. And it does that for each individual cell. So for this one here, where we've got 165.4, all it's done is it's multiplied 216 by 363 and divide by 474, and that gives 165.4. So that's how we can immediately start to say, well, what would we expect to get if there wasn't any sort of bias in the data, adjusting for the different group sizes? So what we're really looking at, of course, is the differences between what we actually got and what we expect to get. We're getting 40 more women in this group than we expected, and we're getting 40 less men in this group. we're getting 12 fewer women in this group, and we're getting 12 more men in this group. We're getting 28 fewer women in this group and 28 more men in that group. So the difference between the observed and the expected is called the residual. Residual just means error or difference, if you like. And chi-square works on the basis of adding up all the residuals, basically. That's what it does. And it says the larger that number is, that resultant number is, the less likely you are to get that by chance, if you like. So what it normally does is it squares the residuals, because some of these are minus numbers, some of these are positive numbers. It isn't calculated exactly this way, but something similar to it. And the squared residuals basically then cancel each other out. So they're all come out as positive numbers, because minus 9 squared is the same as 9 squared. It's exactly the same. So it adds those up, and hence that's where chi-square comes from, the Pearson chi-square statistic. So this is what you get. You get this number at the back, and it says, okay, how often would I get a value as big as that? A difference, which really is the sum of the differences between the observed and expected. How often would I get a value as big as that in a universe where men and women had exactly the same chance of being clerical workers, custodial workers, and managers? And in this case, it gives us a really, really small probability value, p-value. It's so small, it can't display at all. It's actually less than not only less than 0.05, it's less than 0.005. In fact, it's less than 0.001. In fact, it's really, really small. And we're saying that the chance of getting a difference is as extreme as that in a universe where men and women have exactly the same chance of being clerical, custodial workers and managers is so small that you would reject the null hypothesis that the two variables are completely unrelated to each other, that gender in no way affects your employment category. Okay. So the chi-square test here, if we were reporting it, indicates that the probability of obtaining a value as extreme as the one observed is less than 0.001, assuming the variables gender and employment category are unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected. Okay. So why did we choose this example? Why did we choose crosstabs and chi-square? Well, first of all, it's relatively easy to get your head around it, because you can look at the table and you can see there's a big difference there between men and women in terms of the proportion of your clerical workers and the proportion of managers. And you would naturally start to think in terms of what's the chance of that happening sort of randomly, if you like. And that leads you to chi-square, and chi-square works by looking at the difference between the observed and expected and adding that up, and then saying how often would you get a difference that large in a universe where actually gender in no way affected your employment category, and returns a probability value to us, which then allows us to either accept or reject a null hypothesis. And it's very powerful because crosstabs are really simple and they work really well with category data. Now, what happens if the data is not category? What happens if the data is kind of scale data? So it's like, salary and age, something like that, as opposed to salary group and age band. Well, in that case, you come to correlation coefficients. And this is a really nice example of when something is statistically significant, but it's actually not that significant at all in terms of the usual natural way in which we would use the word significance. When is significant not that significant? So the first thing you need to understand about correlation coefficients is that they are illustrated very well with scatter plots. So here we have the relationship between people's starting salary and the current salary. And it shows a really strong linear relationship, meaning that people who start on a really high starting salary, beginning salary, tend to have a really high current salary. And they kind of follow a pretty good straight line. You can put a straight line through this. Now, correlations measure the strength of these straight line relationships or linear relationships. In our example here, we are using Pearson's R. That's Carl Pearson. Carl Pearson's R value. And every point in these scatter plots is a different automobile. It's a different car, okay? And what we're doing is we're measuring aspects of these cars, saying what's the vehicle weight, what's the horsepower. And you can see here, there's some ones that kind of stick out. This has really high horsepower, but the weight's really, really light. If it was that light, we'd expect, we're following a line down here, we'd expect it to be like way, way down here. But in fact, it's a very light vehicle with high horsepower. Here's another one's very light vehicle compared to everybody else, but has really quite, that's quite high horsepower up here. And if we wanted to describe this in a single value, we could use a Pearson correlation value. Pearson correlation value runs from -1 to +1. And the closer it is to those extremes, the stronger the relationship between the two variables. So here we're saying there's a really strong linear relationship between horsepower and vehicle weight, because this is quite close to +1. It's 0.859. You can see here in this one, this is miles per gallon fuel efficiency versus acceleration time. And it basically says that, all right, it takes you longer to accelerate from 0 to 60. But if it does take you longer to accelerate from 0 to 60, then you probably got more fuel efficient car. But here the relationship is much fuzzier than over here. And therefore, the Pearson correlation value is closer to 0. It's 0.4. It's nearly half of this value here. So it's weaker. Here we have a negative relationship. This is going in the opposite direction. It's saying as one value goes up, the other goes down. And here it's saying that if you take a long time to accelerate from 0 to 60, then you probably have quite weak horsepower. You don't have a strong horsepower. Those with really strong horsepower can accelerate from 0 to 60 quite quickly. And so therefore their value is lower. And therefore they have a negative correlation. It's minus points because it goes from -1 to +1. So it's stronger than this value, but it's a little bit weaker than this value. Okay. Now let's look at like a random relationship. So here's mileage against miles per gallon. This is the age of the car, really. As you can see, there's nothing going on in that. It's just a random cloud of points. So it's very close to 0. To say it's a weak relationship, it's basically saying there's almost no relationship there. It's so close to 0. And here we have a negative relationship of -0.67 of engine size against miles per gallon squared. And I've squared it on purpose to show you that the Pearson correlation value only works with straight lines, really. It's looking at the straight line. It's not looking at this J shape. So sometimes you can get quite strong correlations, even if a straight line doesn't fit the relationship very well. You might get a hook relationship here. So that's the thing to bear in mind, is that Pearson correlation values only use straight lines to try and show the relationship between these variables. So after a while, you can show these scatter plots to people and they can start to guess what the Pearson correlation value is, because they start getting used to, what does a correlation of 0.7 look like? What's a correlation of 0.4 look like? -0.7, +0.8, that type of thing. Now, it turns out you can go off into SPSS and you can ask it to do correlations for you. So you can ask it to do correlations. Here we have beginning salary against months since hire against previous experience against education level. And I've highlighted the stronger correlations here. Look, beginning salary is a really strong correlation with current salary. This is this one that we saw earlier on, this one here. This is 0.88, really strong correlation. Months since hire has a really weak correlation against current salary. Previous experience also has a really weak correlation, it happens to be negative. Education level in years actually has quite a strong correlation against people's current salary. So we're looking at each pair. Education level in years has a stronger, even slightly, a quite strong correlation against beginning salary, so current salary. And the rest are kind of weak. Here's previous experience in months. This is quite a weak correlation level, a weak correlation against education level. It's saying that generally speaking, in quite a weak way, quite loose way, that people with more years of education tend to have fewer months of experience than not. So we might ask ourselves at this point, but okay, this is fine. Which ones are statistically significant? Well, in order to interpret that, in order to actually make sense of that, you have to return to your golden rule. And your golden rule is, what's the null hypothesis for this test? The null hypothesis for this test is that the correlation value is actually 0 in the population. Not that it's strong and not that it's weak. It's that it's 0. So we return back here and it says, okay, let's add in the significance values. And the significance values show us that, what's the probability of getting a result as extreme as that, assuming that there's no relationship between beginning salary and current salary. Well, it's a very, very small probability, okay? But down here, we're saying, what's the probability of getting a result as as extreme as, in other words, and I'm using the word extreme here in massive inverted commas because this isn't very extreme, minus 0.097. What's the probability of getting a correlation as extreme as that between previous experience and months and current salary in a universe where the actual correlation is 0? It's saying, well, you'd only get, if it was really, really, really 0, you'd only get that 0.03% of the time, 0.3, 0.4% of the time. So that is less than your alpha level of 0.05, and you regard this as statistically significant. But, is this statistically significant? Yes, because the probability of getting a result is extreme as 0.97, assuming 0.097, assuming there is no relationship between the two variables in the population, or assuming that the correlation is 0 in the population, is still only 3.4%. Does that mean it's notable or worth reporting? No, not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there is no relationship there at all in the population. Doesn't mean it's worth pointing out, in other words. So that is our classic example of when is a significant result not that significant. In other words, with correlation values, people tend to focus more on the value itself and just check that it's significant, rather than on the significant value and ignore the correlation value. This is known as an effect size. It's actually showing you how strong a relationship is. So correlations are really quite strong, quite simple ways to interpret these linear relationships, but they're quite powerful in the sense they can tell us how strong a relationship is. And, if you're talking about something that's relatively strong, most people would say it starts to get more noteworthy above 0.3, 0.4 maybe. It depends on the context. It really does. In natural sciences, you'd be looking at 0.5 or something like that before something started to get kind of interesting and worth reporting. And you would expect them, all the p-values, to be less than 0.05 in those situations. Okay, that brings us to our last example here. We've looked at categories against categories. That was why we looked at chi-square. Then we looked at scale variables or continuous variables against continuous variables. They're not categories. That was why we looked at correlation, because when we look at correlation, all of these are number fields. It's like they're actual numbers. They're not categories. And correlation, what happens when you have a category field and a number field? So what you call a categorical and a continuous variable. Well, then you're normally you're usually looking at averages, usually comparing averages, like, what's the average spend for people in, using promotion 1 versus promotion 2 or something like that. And very often a way to get into that type of testing is to look at something called confidence intervals. Okay. So this returns us back to where our very first example, where we're saying, different samples from the same population vary. Here we can see the mean ages are different for men and women. Repeat a survey or project and you won't get exactly the same results. Calculate a statistic and the results vary from one sample to the next. No statistical calculation can tell you what the actual value of a population parameter is. And we don't know, and we don't have the luxury of repeating samples over and over again. But it turns out we can estimate a range of values that is likely to lie within, okay? Or we have a method to try to capture it. And we can do this by requesting confidence intervals. Confidence intervals are shown graphically as error bars. This is what they look like graphically, where the mean is a little circle. That's the average for two groups. And the intervals is our level of confidence, if you like, about either side of that is shown as these little upper and lower little limits, and look like kind of TIE fighters on their side. So if you do an explore procedure in the SPSS, it calculates the confidence intervals for a mean for you. So you could take like mean age of employee and break that down by men and women. And it will show you the mean statistic. Here it's showing me, for example, the mean age of employee is 34.74. And it shows us the confidence intervals for that mean. It says the confidence intervals that mean is somewhere between 33.67 and 35.8. Okay. These are called 95% confidence intervals. Why 95%? Because we're working with that 5% level again. We're trying to working against that alpha level of 5%. Now, it turns out they're actually quite tricky confidence intervals. They're often misinterpreted. You can often just type into Google what's the definition of a confidence interval, and the first hit you will get out of it is incorrect. I used to do that on earlier versions of this webinar. I think they may have changed and updated the search results, but actually the first hit you got was incorrect. In this example, the mean age happens to be 34.74. We don't know what the mean age for employees is in the real population, okay, that the sample was drawn from. But the confidence intervals indicate that it is likely to be contained in a range like 33.67 to 35.8. As we know, drawing another sample would result in a slightly different mean value. But all our statistics are likely to vary from one sample to the next, not just the mean. So that means that the confidence intervals themselves would vary from one sample to the next. So if we drew another comparable sample and recalculated the confidence intervals, they too would probably be different. In other words, we can't get hung up on the values of those confidence intervals themselves any more than we can fixate on the precise value of the mean. But what we can say is that even if the intervals vary from one sample to the next, they are likely to be broad enough that on 95% of occasions, the confidence intervals will contain the population mean, i.e. the parameter value, the true parameter value. What we should not say is we are 95% confident that the population parameter is between X and Y. That's because the intervals themselves vary from sample to sample. And there's no real scientific basis to the phrase we are 95% confident in this context. It is the procedure that on 95% of occasions will capture the population mean. It's almost as if we're saying we're 100% confident that on 95% of occasions, this procedure will capture the population mean. That's what we're saying, really. And it's almost like the confidence is in the procedure, not in the actual specific intervals themselves. This is a tricky concept for students to get their heads around, but if you want to keep your nose clean when it comes to reporting confidence intervals, this is how we do it. We basically say that we are that 95% of comparable intervals, if you like, will contain the true population mean. Now, how does it work? How does that actually work? Well, it turns out that a special statistic allows us to drive the confidence intervals, and it's called a standard error. And the standard error is just like a standard deviation. When we calculate confidence intervals for a mean value, we use the standard error of the mean. When you're calculating confidence intervals for something else, like a median, you'd use standard error of the median or standard error of a t-value or something like that. So there are other standard error statistics, such as standard error of the median, standard error of the difference, standard error of the correlation. You can use other standard error measures. And these are useful for when we want to calculate confidence intervals for other statistics, not just for averages. But in our example here, we're going to stick to an average. So a standard error is based on the standard deviation. You actually see it here. It's reported as part of the output from the explore procedure in SPSS. And there's the standard error, 0.542. Indeed, just as a standard deviation measures the variation within the sample, so you've all been taught about standard deviations and how they relate to means. Standard deviation tells you on average how much that a value is going to vary about the mean. The standard error measures the variation between samples. So it tries to estimate. It looks at your mean value and it looks at the number of cases you have. And so you got a mean of 34.74. Let's say that's based on 475 cases. That's a reasonably largish sample, I guess, on average. You would expect a mean like that to vary by about half, by about 0.5, from one sample of 474 to another. That's what it's doing. So the standard error of the mean tells us on average how much we'd expect the sample mean to vary from one sample to the other. So if we want to calculate 95% confidence intervals, what we do is we multiply the standard error by roughly 2, or 1.96 to be exact. And that 1.96 relates to the number of standard deviations above and below the mean in a normal distribution that capture 95% of the data. It's kind of a magic number, but we're roughly doubling it. So that means if you take our value here, 0.542, and we multiply it by 1.96, we get 1.062. And all we do then with that 1.062 is we take it away from 34.74 and we add it to 34.74. And that gives us confidence intervals of 33.678, which is here just truncated, and 35.802, which is here just slightly truncated again. Yeah, that's how it works. So it takes the standard error of the mean, which is a measure of how much A sample mean will vary from one sample to the next. It roughly doubles it to give us 95% confidence intervals. If it just wanted to give us 68% confidence intervals, you wouldn't double it. You just add it and take it away. If you want 95%, you double it. And if you want 99%, you triple it, because that's that relates to 3 standard deviations above and below the mean in a normal distribution, which accounts for 99% of cases. So 95% is just the normal one that's used, most common one that's used. And why is that useful? Well, wide intervals versus narrow intervals. Well, first of all, the standard error is based on the standard deviation of the sample size. So the width of the confidence intervals is therefore affected by 2 values: the size of the sample, the spread in the data, the standard deviation of the variable. So confidence intervals start to move apart. They get less confident, if you like, when you're dealing with a very small sample, or you're dealing with a lot of spread, you're dealing with a lot of variation in your sample. And confidence intervals get much closer together when you have a much larger sample, because you can be more confident. It starts to reduce the size of standard error, and you don't have a big standard deviation, because one is the standard error is the ratio of the sample size, in fact the square root of the sample size, to the standard deviation. So when I look at charts with standard errors, I'm really looking at charts with error bars. I'm really looking at charts of 95% confidence intervals. Here we can see, look, men and women here for age of employee, they actually overlap one another. Note that the bars don't quite cover the same range of values. Note that the error bars overlap. Look at the women here. The intervals here for the women are slightly further apart than they are for the men. Why would that be? Either the age of employee distribution is wider for the females, and or the sample size is smaller. Same for the men. Why is their group size, why are their intervals closer together? Either the sample size for the men is larger, and or the spread is smaller, so we can be more confident. But look at the same thing when we look at intervals, when we look at clerical workers, custodial workers, and managers. Okay, so here we can see the clerical workers and the managers, they kind of overlap each other in mean age. But custodial workers, they tend to be much older. Custodial workers tend to be people who are like, caretakers and cleaners and stuff like that. Also notice that the intervals are further apart for them, because it's a smaller sample size, actually, and that will start to drive them apart. Okay, just to finish up, I wanted to illustrate to you how these confidence intervals are created. So I'm literally just going to jump out here and show you a little data set. Here's a little data set I've got. I'm just going to get rid of that. And it's got 3 million records in it. So let's say let's say that this is our population, and we know we get to figure out what the actual population mean is. So if I'm just going to click on this and hit run, we'll see what that produces for us. So there's the population mean. It's 3.33, nice and easy. But now what we're going to do is we're going to run a routine, which will take a subsample of that population, just a random subsample of it, and we'll calculate confidence intervals for it. And we'll do it 20 times. In fact, it's going to take a sample of just 50 each time it does it. So if I hit run all here, there's my population mean. It's going to do it again. Create this population mean again. It's going to create, it's going to take a random sample of 50 cases, and it's going to calculate some confidence intervals for us. And as we would expect, the actual true population mean based on the subsample of 50, it's actually within that little range. There's a 2.33 to 3.99. So the first sample of 15, then the next random sample, it's 2.31 to 3.65, still in there, 2.87 to 4.85. And here's the fourth one, 2.61 to 4.71. We're going to do it 20 times. Here's the fifth one, 2.61 to 4.71. What we're looking for is any intervals where the value 3.33 is not contained within those intervals, because what confidence intervals say that 19 out of 20 occasions, any intervals that you calculate will contain the true population mean. We just happen to know what the true population mean is. And on average, if we would do this again and again and again, we would get to at least one example out of 20. and 20 runs where the intervals didn't contain that value. Now, so far, just glancing at and chatting over the top of it while it's doing it, it looks like they all contain the value 3.33, I think, thus far. And on a few occasions I've done it. Sometimes you'll get two intervals which don't contain it, and you often get lots of intervals being calculated where all of them contain it. You can see this one's getting quite close to it, 3.81. It's very close down to 3.33. Here we are. Here's our 17th example, 2.70. Okay, we've only got 3 more examples to go. Each of these are completely independent of one another, of course. 2.41, 4.23 is sample number 19. 3.51, pretty close, getting quite close to it. And the last one, 2.69. So let's just glance down through it and see if this value of 3.33 falls within every single one of them. I think it does. It's 3.33. It's all within all of them. What's the closest? No, that got up to 3.05. 3.63 got kind of close to it, but they all seem to contain that value. So in this occasion, 20 out of 20, I think, contained the true population mean. If I were to run it again, you might get the same results. You might get all 20, or you might get 18 out of 20. But on average, these intervals, which are completely independent of each other, will contain the true population mean 19 out of 20 times. Okay, so further reading that would be useful to follow up on this, we have a little blog series called Eat Your Greens. You might want to go onto our website and check that out, which will kind of covers much of the ground we talked about beforehand, and also goes into a little bit more detail, like what's standard about standard deviation, finding normality, why is the normal distribution so important when we rarely encounter it in real life, and gives you further reading. Another really good book to bear in mind is David Spiegelhalter's book, which is The Art of Statistics, which really takes people from really the first principles, just looking at averages, and it slowly, very gently starts to take them out through a lot of the concepts we've been talking about today in the last hour. We've also got our own books and stuff that you can download for free on our website. So do check that out if you're interested. In the meantime, with regard to working with Smart Vision, you should be aware that you can source your software directly from us, especially the SPSS software. We also provide training consultancy services and advice and support, both formal technical support for our customers and users of SPSS and related technology. But we also just offer no strings attached advice to people who just contact us for anything related to analytical activities, and we'll do our best to help you. So don't be afraid to reach out to us, even if you're not technically a customer of ours. In the meantime, I hope you find that useful, and we look forward to you logging in again in the future. Thank you.